There we go. All right, so welcome to the 10th episode of Simon and Michaela Play with the API and show you interesting things that you can do with dimensions. Today, we are going to look at how you can use the Dimensions API to do institutional benchmarking and go a little bit beyond just having a look at the aggregate counts and indicators that you can use with the API into doing some more sort of quality associated metrics. So as per usual, the first 15 minutes of the call is just going to take everyone through the Dimensions API itself, give you a basic introduction to that, and then I'll move on to going through the notebook that I've prepared. Just so you can see, there is the notebook in the chat, and so if you want to log in there, you can hopefully have a play around. As I said previously, I've just finished that notebook about 5 minutes ago, so it could be a little rough around the edges, but we shall see how we go. Okay, so dimensions. Here it is. All right, so as I think we've said previously, the Dimensions API is about giving you access to everything that is in dimensions, of course. And the way to think about getting used to the API is just to think about how you would normally search, do a dimension search. So up the top of dimensions, it would probably help if I share my screen. So let's do that. Okay. So up the top of dimensions, we have our search bar. So we would search for a free text word such as plastic, if we like. And we will get some results down the middle. And by default, we're getting results that have the word plastic either in the title, the abstract, or indeed the body of the text where that's available. We can choose to restrict that to title and abstract only, or DOI. So we can do that. When we search for our search result, we can choose the bucket of information that we're looking at. So at the moment, when we do a search in dimensions, we're looking at publications, or we can click across to data sets, or grants, or patents, or clinical trials, or policy documents. And indeed, that's the set of information that we might want to look at. And of course, we can save and export those records to have a look at further. On the left-hand side, we've got the filters. So we might want to refine our results by, if we go back to publications, by year. So we might want to limit our results to year, and maybe open access as well. So you might want to look at the pure gold items. So we've now restricted our results by facets, and you can do exactly the same in the API, and I'll show you that in just a minute. And on top of that, we actually might want to do some analysis over the top of our results that we've brought back. So over the top on the right-hand side, we've got analytical views. So for the same set of search results that I've got, so results mentioning plastic in the last 2 years by open access category gold, we can see that there's a breakdown by FOR code of engineering, materials engineering, and so forth. By field of research, we can see the researchers coming back, the funders, and so on coming through. And you can do exactly the same things, and indeed the API is set up in exactly the same way as the front-end search interface. So you'll know you'll have access to the API, A, if you've requested it, because it doesn't come by default, and B, once you've been given access, you'll see a little workflow tab up the top right-hand side of your menu. When you click on that, you'll see the API entry in the menu bar just here. Now, it's generally the case that if you're at an institution, you'll actually be given a second account to access the API with, and that's because if you're at an institution, you've probably got single sign-on going on, and using an API, you tend to leave your username and password and text fields all over the place, and that's not really what you want to do with your single sign-on credentials. So different username and password for your API makes a whole lot of sense. Lovely. So you can access the API through the application, which is here. It's not, as we'll see today, and as we've seen over the course of the time, the API is is designed to be used in lots of different places and lots of different ways. So it helps you automate your analytical tasks that you would do through the front end. It allows you to move information into places where you would like to analyze it. So we've seen the integration into Google Sheets, and I'm looking forward to seeing what people do with that. Hopefully we can have them on the, do a demonstration on this episode, on one of these episodes later on. And we've seen them in Jupyter Notebooks. On Thursday, we'll see how the API can be used in an R interface. But this interface here is really good for just giving you a sense of what you can do with the API. So if we just have a look at the syntax here, we can see exactly this in the same way that the search bar at the top was looking for publications. We can see our search for publications. And just like we could choose between full data or title and abstract only, you can do the same thing in the API. So search publications in full data 4, CRISPR-Cas9 in this case is our search term. Our filters on the left-hand side in this case are where year is between 2013, 2018, and type equals article, and open access categories equals name, all open access. And we are choosing in this case to return publications. So that's our bucket down the middle of the screen. And we are also asking for information about our, we're also asking to analyze the information, in this case in terms of research organizations and research funders. So whilst I've been talking, you might be wondering what I'm doing. I'm trying to make the search look as much like the front end as possible. So you can see that that's what's going on. And if we run that query, we'll get the results back in a format called JSON, which is a machine readable format, but it's also reasonably easy to see what's going on. So we can see here in the results that have been returned, I'm going to get a bucket of information around funders because I've asked for my funder information. I've got publications, which is that main bucket, and you can see that I've got quite a bit of information coming through for publications. So not just a single line of information, but type, DOI, journal, authors, and inside authors, lots of information about their affiliations, and so on down there for authors. And I've got a final bucket of information about research orgs. So these are the orgs associated with the affiliations of the researchers coming through. So we've got Harvard, Stanford, and so on going down here. So there we've got our organizations coming through. And so that's pretty much the API there. Let me shut my window. There we go. So that's the API. There are a few other things about it that we might want to do. We might want to specify the number of research results that we return. So we can say, I would actually like to get up to 1,000 results. I can skip through the results. So if I want to get the next 1,000 results, I can type skip to the nth result, and we'll see a bit about that, what we do with that today. I can sort by, so I'm sorting by time cited in this case. And yeah, that's pretty much what the API can do. And just with that simple syntax and simple structure, you'll see that we'll be able to do a lot with it. So with that, I will move on to the notebook for today. I can find where I've hidden that. It will be in one of my many tabs that I have open. Try this one. There it is. Okay, so today, as has been the case in many of these demonstrations, we're going to use Google Collaboratory. That is a really nice Jupyter Notebooks interface that helps you share and run Jupyter Notebooks online without having to install anything locally, and it works quite well with the Dimensions client that Michaela has written. I should say, I forgot to say the most important thing about this screen is that once you've got to the Dimensions API screen here from the Workflow tab, you've got easy access to the documentation and also easy access to the Dimensions API lab. So we go across to the API lab, you've got many of the examples that we'll be talking about, that we have and we will be talking about over the following weeks. And each one of these can be opened up in Google Colab, as well as different Python environments. And the other resource that you'll want to use on an ongoing basis is the documentation, and it's written very well. And it's got lots of different information about all the different things you can do with the API. Okay, so with that interlude, we'll step back into the API. This is a Jupyter notebook run in Google Colab. You should have all have the link to it if you want to open it up and try and follow along. So at the start, it's a notebook, and just like most Jupyter notebooks, they are like data recipes. So you start at the top with your ingredients, which are the libraries that you're going to want to use, and you work your way down the notebook cell by cell. So in this case, we're going to use the dimensions client. We are actually not going to use some of these things. They've been imported in from cut and paste, but we will use pandas, which is spreadsheets for Python, quite a lot today. And so we'll start get going with that one. So we'll log in. I'll enter my username. Okay, so today we're going to go through and talk about benchmarking, and the sort of benchmarking I'm thinking about is the benchmarking that I used to do at the University of Melbourne, and that is, can you compare the performance of my institution to another institution by a particular sort of metric? So one of the things that the API allows you to do quite straightforwardly is benchmark in terms of volume. So if you want to say, search publications, return me by research organization, the aggregate publications by count, or by altmetric median, or by recent citations, the syntax is pretty straightforward. So if we do a query like this, search publications, return research orgs by name, you just give me the name, and aggregate, we will get a list of organizations here. And if we sort by count, which you will see the University of Tokyo is up the top there. If we sort by altmetric median, we can see that Harvard University is coming up the top there. Now I've cheated a bit. I've only got the top 20 organizations there. With the analytical facets here, such as research org, you might want to choose to limit that to 1,000 records, and we'll see that we do that a little bit. And we won't put it in the middle of a sentence like that, because that will not work. Put that at the end. Take a little bit longer to run, but that'll come back with a fuller set so that you can rank not just the top 20 results that come by research volume. We can also look at doing a similar sort of search by looking at, when we do these aggregates, we can look at total citations. So that's another way of looking at the results. We can also, and this is quite powerful, look at aggregate research, recent citations, so citations that have happened in the last 2 years, and that's quite a nice aggregate indicator to look at when you're comparing the performance of your institution or an institution that you're interested in to others. So if we have a look here, we can see that it's a slightly different set of institutions coming up the top here based on recent citations in the last 2 years. Now, just an aside, recent citations is quite fascinating to look at all by itself. So if we do a simple query and say search publications return instead of research org year, and we want to look at aggregate by research citations in total, we will see that we get a bunch of publications by year, where obviously the most recent year is 2019 in this case, and then the volume of citations jumps up quite strongly in 2018, 2017 and 16, and then tails off. So if you graph that, you get a nice graph like this. And this is quite important to keep in mind when you're using citation-based metrics, because it really means that the focus of what you're measuring is the performance, more or less, or bias towards this area here, so 2015, 2016, 2017, potentially 18 as well. If you modify that graph and you take the ratio of recent citations to the number of publications by year, you still see the same effect. So it's more flat because you're taking out that big publications curve that's happening. So every year on year, we're producing more publications. But even so, that sweet spot of years between, say, 2015 to 2017 or 18 is kind of there's a certain bias towards that when you're looking at metrics that look at recent citations at least. Okay, so that's a quick rundown of what you can do quite straightforwardly with the API in terms of aggregates and benchmarking. But what if we want to calculate a more complex quality benchmark indicator? So for instance, the number of articles in the top X% of their research category. So in this case, I'm going to look at the number of articles in the top 1% of the 2-digit FOR research categories. So I will start by retrieving the total volume of publications, by research category, I should say. So we will do that. And I am not using the rather convenient filter FOR first, which would be the limiting to 2-digit categories, because that's depreciated. I'm going to use the category 4 account, and that gives me the count of publications by all the different FOR codes. So we can see it's a mixture of 2-digit and 4-digit codes coming up in the list here. So we've got to filter that list down to 2-digit codes. So you'll see I've just used Michaela's DSL magic command here to do a straight dimensions API query in the box. I'm now going to access that result. I'm now going to put that result into a variable that I can use in Python. So I'm going to move to using the Python syntax. So my result is now in DSL query, exactly the same result. And I'm going to filter that. I'm going to process those results so that I can get a level. And so what you'll see that I'm doing here is I'm just looking at the name of the research category. And if the length of that first number is 2, it's going to be level 2. And if the length of it is 4, it's going to be level 4. So I'll just use a bit of Python to do that. So I'm processing the name column, and I am splitting out the name and getting the length of that name is essentially what that piece of code is doing, so that we get that result with the levels in it, which means that we can get our FOR fields of research at 2-digit level here, which is nice. So we've got 22 of them that we are going to do some benchmarking over by institutions. So the second step is to calculate the 1% of the count, because what we're going to do is we're going to use that value to retrieve the boundary record. So in subsequent queries, we're going to sort our results by field citation ratio in this case, and we're going to retrieve the nth record that represents the boundary record, where all of the records above it are in the top 1% and all of the records below it are not in the top 1%. So we get our counts by field of research code. We've got those. And then we're going to calculate the cutoff. So in medical and health, 1% of 114,000 is obviously 11,443. And we've just made them integers, obviously, because we're looking for that whole number record. And we're going to use that cutoff value now to get the indicator value for that 1% boundary. So given these records, we're going to iterate through each of the fields of research. So search publications for category FOR ID that we've got from that query up above. And we're putting that value here. And then we are going to restrict our results just as we did before to year 2018. And we're going to return the field citation ratio. But critically this time, we need to sort by field citation ratio because we've got to order our results so we can get the boundary record. We're only interested in that one record that is the boundary record. And the way that we're going to get there is we're going to use the skip functionality in the API. So this is actually a reason where you do need to use all of the nice little features of the API. So sort by returns the results in the order of field citation ratio. Limit, we're only interested in the first record returned, and skip, we are skipping to the boundary record, and that gives us our cutoff record. Second thing to note, the strategy that I'm talking about today will only work when the boundary record is that says greater than, is less than 50,000 records, because then we're going beyond what the API can return. There are strategies that you can employ to do that, but it becomes far more tricky. Okay, so we will run our query I better run it because whoops, it's because I haven't run something up here. I'll just thought I was being clever by skipping steps, but it is never clever to skip steps, because just like you skip steps in a recipe, things go bad. Okay, so we will get our cutoff records. So it's going to do a query for each of the 22 two-digit field of research codes. So we've got those now. And the other thing you'll notice here is I'm creating a list. And in that list, I'm going to append each of my results. So now I've got a list of queries in data frames, and you can see that to get that back into the one spreadsheet or the one data frame, I'm going to concatenate that list together, which is what I'm doing here. And now we can see our cutoffs. So we can see here that we've got the field citation ratio cutoff for medical health sciences. In 2018, for the top 1% was 24, in engineering it was 18, in physical sciences it was 20, and so on. Okay, so the reason they're integers is that the API syntax only when you filter for field citation ratio in the body of the API, you can only use integers or strings. In this case, it's a number, so we're looking for integers. Okay, so we will move down. Okay, so we've got our cutoff values. So we're now going to go through and get the organizations, the top 1,000 organizations, and get the count of number of publications that they have in the top 1% of their category using that boundary record. So we've got that field citation ratio that we've calculated previously. So we've got search publications where category is defined from the list above, and the field citation ratio is the cutoff value, about the boundary record for 1%, and we'll get our research orgs.
All right, hang on a second.
Okay, so I've got my records. So I've got my records, I can now rank them. So I've now got the number of publications in the top 1%. So the way that I can do a ranking using pandas is quite simple. I just use a line like this, and basically what that is saying is group my results by field of research name, and we want to rank on count. I want to rank the results ascending equals false, because the higher the value, but the lower the rank. So if I do that, I've got my list, and now if I have a look for an institution, we can see that we've got, for the University of Melbourne, we've got ranks of their, according to this rank, globally, it's 22nd in the world in terms of number of publications and top 1% globally, 141 in the world engineering, and so on. We change this to Cambridge, we can have a look at different institutions and see how that goes. Now, there's still a problem with this rank in that if you're a large institution, and you're pumping out thousands and thousands of medical publications, it's quite easy for you to get the volume of 1% publications, or reasonable that the amount of publications that you're doing that meet that quality threshold are going to be larger. So there's still a volume effect going on with a measure like that. So we should probably control for volume. So what we're going to do now is look at the ratio. So the ratio of publications in the top 1% globally compared to the total number of publications that that institution is producing in that field of research. So again, we're going to use that same pattern, and we're going to cycle through. In this case, we're not going to look at the records that have been cut off at that boundary level and return all of them. So pretty much exactly the same query though. So all we're doing now is getting that total number. Okay, and so now we've got our total number. So we will create a data frame called all publications, and we will pop that in. Turn my notifications off. Oh, they are lovely. Okay, and I'll join them to my results. So now you can see that. Okay.
Excuse me, may I ask a question?
Sure can.
Yeah, on line 235, does that PD concate means that you actually concatenate DF1, the 3 columns in the DF1, ID, for ID, and count? So sorry, I'm not super familiar with this syntax.
Yes, so it is concat. Yeah, you're exactly right. It's concaten. So within that, the list that it's concatenating is a set of data frames that have been returned in the loop up here. So this loop is going through, and really so the first one is going to be medical health, the second one will be engineering, and so on.
Cool.
And so that PD cat is basically joining all of those spreadsheets together.
Okay, sounds good. Thank you.
Yep. And this actually isn't affecting the concatenation. It's just saying, actually, I really only want these three fields from the results, because I'm going to join them back up to the spreadsheet.
Okay, gotcha. Thank you.
Cool. So now I've got my spreadsheet, I've got my count and count all. And so I've got enough information here to create the ratio. So the next thing I'm going to do is I'm going to calculate the percentage in the top 1%, which is 100 times the top institutions all count divided by, the count of top 1% publications globally divided by the total number of publications. So I'll grab that and I will go through. Now these results are also going to look a little strange. So if we just now have a look at the where the University of Cambridge ranks in these results, suddenly it's ranking 43 in medical and health sciences, 136 in engineering. That looks a little strange. If we have a look at it, I have the same set of results by a particular field of results. If we have a look here through medical and health sciences, again, this is a fairly strange, filter on, a fairly strange list. So we've got Broad Institute, well, it's definitely a medical institution, but then we've actually got companies coming up here. And so what's happening here is smaller institutions are being preferenced too much. So if you've produced, to take an extreme account, 10 medical publications and 2 of them are in the top 1% globally, then you're going to have a really, really great percentage of top 1% articles. So we need to control for size. And so we've got to do a couple more steps to do that. So what we're going to do now is, the way we're going to control for size is think about it from the perspective of an institution. So if I'm the University of Melbourne, I'm not really concerned about what the performance of an institution that produces in total a far smaller volume of publications in a particular field. I'm really looking to understand how I can better my performance in relation to other institutions that have similar setups and similar structures to me. So I'm interested in publications that produce probably at least the same amount or more publications in a particular field. So I need to actually apply a cutoff score. So the first thing I'm going to do is I need, and that means that from every institution, I will need to calculate a relative ranking. So what I'm going to do is I'm going to join the set of institutions back to that set of queries. So now I'm going to have a complete set of institutional performances linked back to each institution. So, and from there, I'm going to filter it a little bit more. So we're going to join our set. So now we've got a relative ranking for the University of Melbourne, or at least all of the institutions in that list. Can never quite predict when Google Colab is going to go slow on me. So you can see we've now got a table here with a reference ID, University of Melbourne, the reference count for how many publications University of Melbourne has produced in that field, and we can compare it to the number of publications that, in this case, the University of Toronto has produced, and so on down that list. So we can compare these two numbers. So if we go down now, we can start to process this information so that we can look at the set that we like, that we're interested in. So in this case, we're now going to filter that relative ranking, and we want to identify where we want to filter it so that we want to get rid of the records in that list that for relative to an institution produce less publications than they do. So we will filter that list that way. And then we want to rank those publications respectively. So we're going to get rid of all of those smaller publications. So now we've got our list of publications relative, in this case, to the University of Melbourne. And so we can see now that as different from before, when we were looking at the just pure volume ranking, where I think they are ranked 24, actually they're ranked probably about 14 in terms of the institutions that they're interested in bettering their performance against. So that's quite insightful. So finally, we might not just be interested in the single rank for a particular institution. We might be interested in the institutions. We might be able to extracting the list of institutions that say in this case, the University of Melbourne is interested in comparing themselves to. So for that, what we will do is we'll filter our list a little bit more, and that final rank that we've got there, we'll just use pandas to identify the 5 institutions above the University of Melbourne in that ranking and the 5 institutions below in that ranking. So we will, to do that, we will add our rank cutoffs again to that list so that we can compare the results and calculate a rank difference, which is the filtered percent rank subtracted by the the filtered percent rank of the focus institution. So now, if we have a look at the list, we can say, okay, for the University of Melbourne in medical and health sciences, which institution should I be interested in? And in this case, it would be above me in terms of volume and percentage in the top 1% globally at Johns Hopkins, University of Washington, Texas, Yale, and UCLA. And below are Toronto, Michigan, Emory, Sydney, and Sao Paulo. If I look at Monash University, you can see above there's Emory, Pittsburgh, Michigan, Toronto, Melbourne, and below. So that list is relative. So what I think is quite nice about that is that it's not a universal ranking. And in fact, universal rankings are in some way not particularly useful for institutions in terms of understanding how to better their performance, but we can actually provide a tailored list of institutions using the API for different fields of research. So if I wanted to change this to look at environmental sciences, then I'll just change the forename in here. And the recommended list of institutions for environmental sciences that Monash should be really thinking about is this set above and below. So that is pretty much my take on how to use benchmarking with the Dimensions API. And I think we've got a few minutes to spare. So I've lost my little widget with questions. So if you've got a question, just shout out, because I can't find where I've hidden my little chat box. Ah, there it is.
Hi, Simon. Thank you very much. I would like to understand more about the boundary limit, which because I haven't got a lot of hands-on experience on that. Would you mind to elaborate a little bit more on that? Thank you.
Yep. So if you take the question, and so that I'll go to the top. So the question would be, how many publications has my institution produced that are in the top 1% of the world as defined by a particular metric? In this case, I've chosen the field citation ratio. So
I guess it's because there is one line you show that the strategy wouldn't work if the boundary limits more
oh,
than
yes,
50,000.
got it.
Yeah. So is that 50,000 for all the API or?
Yeah, so the reason for that is that the way that we're getting the cutoff record is we're using the skip functionality of the API. And the API itself is limited to return you the first 50,000 records of the query.
Okay.
So if your cutoff is beyond that, then you won't have access to the information that you need. Which means that, for instance, if we have a look at medical and health sciences, we can do top 1%, but we can't easily do top 5%. I have thought about ways that you can do it by iteratively getting the first 1% of records, for instance, removing them from the set, and then getting the next 4%. But it gets much more tricky to manage. It's certainly possible.
Oh, okay, gotcha.
But another way, it is a problem in terms of there's so many records in medical and health sciences. But if you see for all of the other fields of research, you could easily calculate a top 5% category. And indeed, if you went down to the 4-digit level, you probably wouldn't have any problems at all calculating a top 5%.
Yeah, okay.
Level.
Okay, I understand. Thank you very much. Thank you.
No problems.
Hey, Simon. This is Dale Hess at Rochester. How you doing?
Yeah, good, thanks.
I have an interesting question on this. I've tried to do some of this work myself. And one of the challenges that I've run into is that some institutions have a separate grid identifier for their medical school. And so I'm wondering, how would that play into an analysis like this? It's almost as though you need to aggregate the data across multiple grids for institutions that you want to compare to.
That does get it's certainly much trickier, and my brain can't do the gymnastics on the spot to work out that one. But you would need to aggregate your results. So that would be one thing. The other way to think about it, I suppose, if you've got a medical school, it may be, if you're ranking by a field of research category that's sufficiently targeted to only pick up results within a medical school, then that'd be one way to mitigate that. So, for instance, if you had a medical school and all of your medical research was being done inside that medical school, then that problem would go away. Of course, you've still got problems where a particular field of research is being done both in the medical school and on the main campus. So that's still quite tricky. But yes, you're right that just doing it by the grid ID will be a little bit more tricky when you've got that scenario. Michaela, have you come up across that?
Not really. I think your answer is what I probably would have said. It is tricky because you need to do some aggregations before doing all these calculations using the grid identifiers. But I cannot think of any other solution off the top of my head.
Yeah, I think your code just gets a little bit more tricky. So we've just gone through and we've used the the aggregates return research orgs. Essentially, instead of getting those numbers for each, where are we? Numbers for each research org here, you would need to create a list and a loop through and almost get the values for each research org out separately. So instead of getting 1,000 at a time, you've made your query much larger than that for those, at least for those specific use cases. So in fact, what you could do probably is benchmark all of the institutions that don't have the combination of medical school and main campus, and then create a separate loop to get out the values for those institutions and join that back to the query. But there is no way around getting it. It makes it far more complicated.
Okay, thank you. A lot of it is our fault because our researchers sometimes put our medical center down for the affiliation, and sometimes it goes down as the university itself. And so we have this hodgepodge of researchers scattered across 2 different grids, and that does make things a little more complicated. And I don't know how common that is across your universe of institutions within grid. Do you have a good feel for that?
I think it's a peculiarly US problem, which is to say that's no small slice of the research environment. But internationally, a lot of institutions roll up more neatly, so to say. But yeah, there is no getting around that. It's a problem across multiple institutions, I'm sure.
Well, that's great. Still very helpful. Thank you very much for doing this. Appreciated.
You're welcome. Excellent. Well, in that case, we are right on 4:15, so I will stop the screen recording now and wish you all a happy week. And don't forget to come next time when we see, we've got Michaela, would you like to tell us a little bit quickly about next week's?
Yeah, this week's on Thursday.
Right, yeah.
So we're going to have a guest speaker, Massimo Aria from University of Naples. He's developed essentially an R version of the DINCLI library for accessing the API. So DINCLI is this library we have for Python. We know that many research analysts and in general data scientists, they use R. It's very popular programming language for statistical analysis. So we're very thankful to Massimo for doing this. And so that's why we invited him to essentially showcase and show us how that works. So please come along on Thursday as well.
Lovely. See you all then.
Thanks, Simon. Bye-bye.